for the energy transition to actually happen, we have to digitally transform. And that means we need to think of not only moving electrons in terms of a voltage and current, but we have to think about monitoring the grid continuously in high resolution. It's about moving bits as well as electrons. Mm-hmm. And like that has to happen. Otherwise, the energy transition is DOA.
Hello everyone and welcome back to the CleanTechies Podcast. This is episode 55 of the show. I'm your host Silas Maynor and I'm thrilled to have the opportunity to bring this episode to you, and I'm very thankful again to you for tuning in as always. Before we get into the details of today's episode, we of course ask that you subscribe, turn on notifications, and let us know any questions that you do have to be asked in future episodes, or specific topics, or perhaps specific founders, perhaps yourself included, that you'd like to have on the show in the future. And then of course, as always, we want to highlight what we can do on our end. If you're a founder with specific needs, we are glad to make any introductions that we can. Again, usually this is around capital or partnerships or talent, but anything goes essentially, since our entire goal is to help founders in this climate tech space to expand and to be successful in their businesses. So please do consider reaching out if there's any way we might be able to help. All right, let's get into the details of today's episode. So today we are speaking with Sean Murphy, who is the CEO of PingThings. PingThings is, in technical terms, the world's fastest nanosecond-precise time series analysis and AI platform. It's a mouthful. But to translate that into English, they are able to essentially analyze vast amounts of data very, very quickly. And the application they are focused on currently with this technology is for utilities and grid operators. Specifically, transmission lines have a lot of sensors that are not used because most utilities didn't have the ability to actually read and kind of utilize the data that could be collected from those, from that hardware. So with their technology, they are now able to help do this, and it can have a massive impact on the grid and on climate change in general, by being able to understand kind of what's happening, especially kind of as regards to wildfires and many other ways. So as usual, we discuss a lot of things ranging pretty widely from his inspiration to become an entrepreneur, how their technology works, future trends. One thing that was quite interesting was a misalignment of incentives amongst the utilities. And of course, as always, we discussed the education space in general. So really, really fun conversation. I really appreciate everybody tuning in. I'm sure you're going to enjoy it. Before we do get into the show, of course, also want to make mention to our sponsors, NextWave Partners. NextWave are experts in talent acquisition, recruitment, and retention across the climate tech, renewables, ESG, and technology spaces globally. So if your team is growing or you personally are looking for a career change, you can consider reaching out to NextWave through their website, next-wavepartners.com, or reach out to one of their consultants directly via their LinkedIn page. So without any further delay, let's get into the show. All right, welcome to the show, Sean. How are you doing today?
I am doing well. It is a beautiful day in the nation's capital.
It's also not too bad here in New York City either. I cannot complain. I think it's going to be like something like 67 or 70 all day, which is my favorite temperature, and sunny. So I'm really excited. I'm really excited to have you on the show. I think that this is going to be a very technical one and something that I'll probably learn a lot in. So why don't we just start with you kind of giving us your background, who are you, and what you're doing a little bit, and then we'll kind of get into how you got into the space.
Yeah, so I'm Sean Murphy. I'm the CEO of PingThings, and I mean I've had a fun journey. I was very technical early on in my career. I was a senior research scientist at Hopkins, and I did all my grad work in biomedical engineering. So I've been working with kind of what was considered large amounts of time series data. But I was writing code in C for performance reasons. And I was also doing a lot of high performance computing back then as well. And then I left, I went and I did my MBA, my master's of bullshit and alcohol abroad. I kind of got tired of writing papers had very little fulfillment. You know, how many people in the world actually read this? What type of impact do you actually have? So I went off, did my MBA, and I wanted to become an entrepreneur. And just for your listeners listening, don't do that. Like, you don't learn to be an entrepreneur in school. Rookie mistake. So after I got the degree, I started building companies, and each company was kind of an order of magnitude more successful than the last one. And so my previous company was a relatively successful data science and analytics consulting firm, kind of helped create value from data across different industries, which was very fun, highly educational. And now, I guess PingThings is my fourth company after my business school.
Interesting. So could you, I guess, I'm always curious, especially with people who are very entrepreneurial nature, and especially yourself, you've done a number of things here. What when do you feel like you knew that you wanted to build businesses, and what kind of, I guess, inspired that early on?
Ooh, so I think you have to kind of go all the way back. I'm from sort of the middle class. I went to a state school, like the nearest best state school that I could, which was the University of Maryland, College Park. And, my worldview was very small. It was very limited. I had inherited sort of the views and understanding of how the world works from my parents, who had actually been poor growing up, and also like your peer group. And I didn't even know what an entrepreneur was in college. I knew I was good at science and math. The whole Silicon Valley tech boom was happening when I was an undergrad, and I had no idea. I didn't even know it was a thing. But when I got out into the workforce, I was always a little bit of a malcontent. I always, there were better ways of doing things. Why weren't we doing those? I always had a lot of ideas of that, at least pass the initial sniff test, and I wanted to kind of push, wanted to build. And that was, I don't know, I didn't have an outlet for that. I didn't know what to do with that. So it took a little time, but what I did is I slowly convinced myself that I could make money without a W-2 job, right? I'd grown up with, like, a job was everything, your source of income, your how you eat, it's everything, right? My parents had that scarcity mentality, and I had to prove to myself that I could sort of get out there on my own without a W-2 job, hunt and eat what I killed, and actually be successful. And so I had to do that for myself. And then as I grew more successful doing that for myself, then you naturally, as you get good at that skill, you then bring more people into the fold. And lo and behold, you're building not just your own life, but like companies that are supporting other people's lives. And so that was kind of the trajectory, but it was very incremental. I had to prove it to myself before I would take the next step.
Interesting. So I guess I'm kind of curious. I feel like there's a lot of people who are probably in this boat. Is how did you, maybe how many years did you spend kind of working in the professional field, trying to kind of figure out your way, and maybe let's just say there being friction in terms of how you felt you fit in and whether or not it was a good place. How many years was that, and how did you navigate that early part of your career where you still had a lot to learn, and then you eventually got to a point where you decided, ultimately, I know enough to go do this on my own? Could you just walk us through that timing and how you thought about that and kind of how you navigated that? That'd be very keen. I'm personally very interested to understand that.
Yeah, absolutely. So when I got out of undergrad, my big game plan was to go to med school. So I took a job at Hopkins, just as a holding pattern. I came out of undergrad. I got a job that I thought was interesting, but I was only going to be there for a year because then I was going to go to med school. And I actually bailed on med school and decided to go down the biomedical engineering, the academic grad path. And while I was working full time, and so I was kind of like straddled between two worlds, like trying to, continue to achieve academically, but then also maintain this full-time position. And I was in that role for, let's say, a little under a decade, approximately, well, let's say 8, 9 years. And the interesting thing was that while I was doing this, I was trying experiments outside of that, right? Me and my buddy tried a little bit of a real estate hustle, because we'd both purchased houses and we were renting stuff out and we're seeing if we could buy more houses. That failed spectacularly, but educational. At the same time, I was uh, very passionate, committed to as an amateur dancer, and started teaching. And so I was coaching around local dance studios and colleges. And that was actually pretty instrumental because I could go in and I built up classes and I built up a little following of people who would pay me money and outside of a W-2. And that was very eye-opening. So kind of those experiences plus some of the new people that I were now part of my life who had come from vastly different socioeconomic backgrounds, I learned from them as well that, you know, there's a lot more out there that I just never conceived of.
Hmm. Interesting. Yeah, I always find this very fascinating because I think this evolution is difficult for people. It's almost like kind of understanding at what point do I become, I guess, unable to stick around and figure and work for somebody else. You know, once you kind of get a taste for it, it's really hard to get rid of it essentially. So that's very interesting. Um, I guess I'm curious. So maybe let's move in a little bit more to what you're doing now with PingThings, and could you help us understand exactly how the evolution of deciding to launch this came to be, and we might have to dig into some of the technical terms as well.
Yeah. So what PingThings offers is a time series data management, data analytics, and AI platform. So, you know, obviously for the last 20 plus years, there's been this spate of big data platforms, Hadoop, Spark, etc. These platforms that are really designed for large amounts of data. And some of them are more general purpose, like you can leverage them for all types of data. And when I say all types, I mean everything from text to numbers to video and audio streams, and then time series data. And then for us, for PingThings, we focus on a very niche problem. And that is what happens when you have a large number of time series data streams that can be, each data stream or each time series can be very dense. It can have a very high sample rate. So just to kind of explain that a little bit more, especially in engineering backgrounds, in the industrial world, when you're sampling or measuring the behavior of a machine, you're doing it at a regularly spaced interval, once a minute, once a second, or sometimes once every 10,000th of a second. And you're taking that measurement, and the faster you sample, often the more information you get about the underlying processes that are impacting that measurement and the machine's behavior. So we built a platform that could handle very fast time series data from a large number of sensors, so hundreds of thousands or millions of sensors. And this for us was actually pretty interesting because it wasn't a problem that, if you look at the, you know, FANG, if you look at Facebook and you look at Google and you look at kind of the big tech companies, they're not as, this is not as critical of a problem to them, but it is to folks running the electric grid, for instance, or fleets of electric vehicles, or actually in healthcare, this is actually quite needed. So that was kind of the problem that we were solving for, which allowed us to design and build a very, very, very fast and scalable platform. Even with a small team, even with not, without tons of money, we were still able to do that.
And so when you started this, I think those technical terms seem pretty understandable, but I want to move on maybe a little bit to once you started this and kind of started developing and finding a way to make this possible. How did you settle on an industry to work with? Obviously, you mentioned the power grid, and it seems as though you didn't have a whole lot of involvement in that in the past, if I'm not mistaken. So I'd be keen to understand how you decided which industry this would be helpful for.
Yeah, that's a great question, and part of it is, I guess it's somewhat random chance in that we received money early from the Department of Energy, really ARPA-E, the Advanced Research Projects Agency Energy. And because they saw this problem as critical for the grid, based on kind of projecting out how sensors were being developed, and they were increasing sample rates, and we expected a kind of a much greater proliferation of sensing on the grid. So given that projected future, we needed capabilities that did not yet exist, and it seemed like a really strong opportunity for us. So that's how getting money from ARPA-E was a big influence for us. And I always joke that like friends don't let friends sell to electric utilities because of the notoriously long sales cycle. But ARPA-E was very, very helpful getting us going.
Mm-hmm. Yeah, I can imagine also the influence of the people around you and the kind of the maybe mentors you had, given that relationship was probably also strong and led to that. So that's very interesting. I guess, is there a way you could maybe break down kind of to help people visualize how the data works? Because I want to understand the exact problem you're solving. If you can I know there's a really interesting video on your website that it kind of does a demonstration. If you could somehow kind of explain that, would be really helpful.
Yeah, so really one of the key things to understand is that, right, if I have 100 streams of data coming in once an hour, it's actually not that much data, and I can probably stuff it into Microsoft Excel, God forbid, and do some analyses there. Because the amount of data is not, it's not hard. I save it on my hard drive and life is good. I don't even think about it. The tooling that I need is available. However, if I have 10,000 sensors, each one generating 50 streams of data, and each stream is sampling at, say, 60 measurements per second, Excel doesn't work. And a lot of the big data solutions that exist actually break down. There are ways that you process time series data, ways that you think about time series data that aren't well supported in a lot of those generic tools. So if you use kind of insert generic big data framework, you have to spend a tremendous amount of time building out tools that allow you to work with time series data in a way that's relatively natural to the subject matter experts and data scientists who use it. And so for us, our goal was to make it trivial to handle very large volumes and velocities of this data so that we could build use cases and applications from all of this data that matter to our customers.
And so I guess, is there a way you could help describe how you ended up solving that problem, maybe from a metaphorical standpoint, using the streams of data or whatever, to help understand exactly like the principle of how you're able to do that? Was it a hardware innovation? Was it a software innovation? I'm kind of keen if you're able to share.
Yeah, absolutely. So so as I mentioned before, right, as you increase the number of streams, as you increase their sampling rate, the amount of data you are ingesting and you're storing it over time, it outstrips the capabilities of a single machine. So when you look at a lot of legacy solutions in the industry, well, like they did one of two things. well, you were stuck with whatever a single machine could handle, or they sold you on a much larger server. And what we did is we applied a lot of contemporary best practices in building out distributed systems, and kind of building for horizontal scalability so that we could, oh, we have more sensors, we're going to add another compute node. We're just going to keep adding nodes so that we're horizontally scalable from the beginning. So from the very beginning of the platform, we designed it to be a distributed system. So our smallest version was 3 compute nodes, and we scale much bigger than that. So whereas other folks kind of built for, oh, I have 1 computer, and if I need more, I'm going to make it bigger. What we did is we built from the ground up, kind of using best practices borrowed from like the Googles of the world. And so we built a contemporary, modern, high-performance platform for time series data that's scalable, that's cloud-based, that's, my biggest customer, we have over 1 petabyte of data. And that was very powerful. And our, not only our ability to ingest, but how we store data. We store data in a distributed fashion across many, 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 many drives and many different types of storage, so that we can offer like near very, very fast access. Queries typically respond in under 100 milliseconds and give you arbitrary access to both real-time and historical data. And that was a very hard problem that I think we've done a good job solving, that it gives us sort of performance advantages that other folks don't necessarily have.
Okay, interesting. And then, so maybe what is a specific application or a task or action, I guess you'd say, that the utilities usually were having to do, and how are they solving it before, and now how are they solving it now that they have your software?
So, and this is a great question. We always get asked about the use cases and applications. And I'm going to turn this question around, and I would say, on your smartphone, what is the killer app? What is the use case for your smartphone? What's your number one?
I mean, there's a lot, probably in my phone, because I call a lot of people.
Right, you call, and you probably use it for navigation. Oh, and you probably live stream and some games, and there is no killer app. There's no one use case. There's actually a swarm. It's like a whole giant collection of use cases that are valuable, that make the phone valuable. So we think of that way about our platform. There's not one killer app. There's not a Lotus 1, 2, 3 that, oh my gosh, we have to get this. It's all of a sudden, and you look at the contemporary grid, right, on the distribution system, when you have smart meters deployed, and a lot of smart meters aren't universal. So not every house has one, but when you have a smart meter deployed, the utility gets a measurement, or actually 2 or 3 measurements from my house once every 15 minutes, sometimes once an hour. My platform handles data like 10,000 times faster. So imagine all of the interesting things that happen between those 15-minute samples. They don't exist. They can't see them. The utility is blind to them. So all of a sudden, when you enable the customer to work with data that's orders of magnitude faster, the first thing that happens, the first use case, is they see things that they had no idea were actually occurring on their grid. Oftentimes, those things are very impactful. They'll see oscillations or harmonics that are impacting the lifespan of important equipment. They'll see transients that could indicate a problem in a distribution line, or a problem in a transformer or smart switch or smart relay. So all of a sudden, it's like going from AM radio to high definition television. The amount of information being communicated is much more, so they can actually see what's happening.
So then what would be some of the, I guess, because obviously for the purpose of this podcast is to understand how the impact can be in helping the, I guess you could say, energy transition, the green movement towards a cleaner climate. What are some of the impacts that this can have, whether it's for the grid or others, right? When they find this data, what will it allow for them to do? Like, what are some of the improvements that can happen? I'm just kind of curious to hear several of the examples that you think of.
Yeah, and they're massive, and like um, they're massive. So one example is when you think about wildfires, right? The wildfire that gets initiated by many different events on the grid. So you can have an example in high winds. You can potentially have conductors actually hit against foliage like a tree, or even sometimes they can hit against other objects, and that can cause molten debris, ejecta, to be emitted from the power line, which then obviously molten metal hitting the ground can initiate a forest fire. And those events are very brief, right? When that conductor hits the tree, it doesn't last for 20 minutes. It doesn't touch that tree for 20 minutes. It's a very fast transient that you can only see if you're sampling the data quickly enough. And so detecting those types of events and localizing them exactly where they happen are the types of capabilities that we enable. As another example, if you look at solar, right? Solar power generates electricity, creates a voltage across this semiconductor, and these are inverter-based resources. To connect solar to the grid, you have to convert the power that's being generated into a nice sinusoidal waveform that gets synced up and pushed back into the grid, which, right, the grid, when you transmit power, you're doing it not DC, you're doing it AC, you're doing it as a sinusoidal waveform in the US at 60 hertz. And so these solar cells or solar plants, they're inverter-based resources. They have these inverters that help do this matching. And the problem is that these inverters create a good number of problems on the grid. They create a good amount of high frequency noise. They can cause oscillations and harmonics. And we're getting reports from a lot of utilities that they need help localizing and determining which of these inverter-based resources are problematic, so that they can work with the asset owner, and maybe the hardware gets replaced, maybe it gets upgraded, maybe it gets fixed, but they can resolve these problems before they cause much more significant impacts to existing grid equipment.
Mm-hmm.
So the ironic part is, as we roll out a lot of green, clean energy, unfortunately, there are adverse impacts on legacy equipment that you need to be able to distribute all of this power.
Mm-hmm. Interesting. So just to clarify, so I understand this correctly, when you mentioned the harmonics, and you're just talking about the specific things that the electricity, the way it's created, creates this kind of adverse effect that is going throughout the grid and causing other dilemmas. Is that correct? Because I'm not an electrical engineer by any means. So I'm trying to understand this a little bit.
Yeah. So without getting too deep into the weeds, when you have a 60 hertz, so 60 hertz being 60 samples, 60 cycles per second. So every second, the voltage and current waveforms are oscillating 60 times. It's a fast waveform that when you have a solar plant, you have to match that waveform to push your power back onto the grid.
Mm-hmm.
And if you don't do it properly, it can have all sorts of impacts and ramifications and it can create these transients, it can create oscillations, it can create harmonics, which are power or in the 120, 180, 240 sample per second frequency bins. So you can create unintended consequences that have pretty significant impact on old legacy grid equipment. And it's interesting because if you look at the original grid, the best explanation I ever heard was you can think of it as a volcano, right? We had these big generating sources like a hydro plant or a coal fire plant, and these massive turbines spun and the generators created electricity that then flowed over the transmission lines to the distribution system and was consumed.
Mm-hmm.
It's a very stable, very, I don't want to say simple, but it's like a volcano. Lava erupts from the volcano, it flows down the volcano side, and then it covers the island and goes into the water.
Mm-hmm.
And there's not much in the way of instantaneous feedback and control to the volcano.
Mm-hmm.
But now, so you have a system that was designed for that model, and now all of a sudden you're adding fundamentally different kind of power sources, like a solar plant or a wind farm, or even like battery storage or other types of storage. And then you're putting solar panels on rooftops, on individual rooftops, and now all of a sudden that grid that was designed for a very different set of circumstances now has to be adapted to a fundamentally different system. And
Mm-hmm.
we're trying to do that when at the same time, like all of that like legacy equipment, all of the existing transmission system and distribution system, a lot of those assets are decades old. Many of them, especially on the transmission system, they had a expected lifespan of 40 years, and it's they've been in, this is a 60th year of operation.
Mm-hmm.
And
Interesting.
so we have this grid that's, I don't want to say it's past its prime, but it was overbuilt, luckily, and those assets are still functioning, but they weren't designed for a lot of the stresses and strains that we're now putting on it. And as solar and wind and other renewable resources increase, that's going to stress these critical legacy assets even further.
Mm-hmm. So I guess there's a couple things I want to clarify here. So what do you think, given this problem, what do you think the solutions are going to be? Is it going to be primarily companies being able to implement a software like this so they can start to identify the problems and then just go, clean up and fix the equipment ad hoc? Or do you think that there are other solutions that can help kind of retrofit some of these to reduce the costs of any kind of, major, exchanges of this equipment?
Oh, so I think you're going to need both, but right, the cheapest thing to do is actually to do this in software. If you can do it in software, you do it in software, right? Software is eating the world because it's inexpensive, and it can also be very powerful. And so, what we envision is for these problems, if you have access to higher frequency data, so you can start to really understand the behavior of the grid, and you can do that at a time resolution that is not once every 15 minutes or once a second, but like 10,000 times a second, you can actually see what's happening, and you can localize and identify the problem spots that either need to be fixed or replaced. And you can do that with a precision that you simply just can't do now. And,
Mm-hmm.
and that's key. Imagine if you went into a hospital and you're like, hey, I have something with my heart, it's wrong. And the doctor takes out, grabs your wrist and takes your pulse and says, hey, your pulse is 80 beats per minute, you're fine. Like, that would not be acceptable. You'd be like, no, my heart's wrong, I swear. And what you'd want is an EKG at the very least, and an EKG typically they sample at about 1,000 samples per second. That gives the doctor a lot more insight into the specific fast behavior of your heart, so they can diagnose the problem and get you on your way to being healthy.
Mm-hmm.
And it's the same idea with the grid. We need an EKG. We need higher frequency sampling, and then we need the software that can interpret and understand that added information.
Mm-hmm.
And we need that now. We don't need that 10 years from now.
Yeah, because otherwise you can't identify where the problems are to solve them and to fix them. So I guess the other big question that comes up with that is, are there any devices that have to be installed in these transmission lines to be able to collect this data, or is this all already available? You just kind of integrate with what they have existing?
So the beautiful part is that a lot, especially on the transmission system, manufacturers 20 years ago started to embed higher frequency sensing into the assets that they were selling, right? If I'm selling a $500,000 piece of equipment, and the bill of materials for that sensing is $1,000, well, I'm just going to add it. Why not? And so the interesting thing is that there are hundreds of thousands, if not millions, of higher frequency sensors on the transmission system. Most of them are turned off. Most of them are not streaming data. So when we go in and we work with the utility, like one of our customers, they went from 200 of these sensors activated. Now I think we're close to 1,000. So because the customers can't handle that type of data now, they turn them off. They're in the dark.
Interesting. Okay, so it's actually, it's quite fascinating if that part of the problem is essentially solved, right? Because that's not a CapEx that they have to afford at the beginning. Then if most of their equipment already has these sensors on it, that's quite interesting.
Yeah,
some good forethought on these engineers' parts, right?
Well, it's funny, right? Like it's the competition between these asset manufacturers that's key. It's the competition that really drives it. And unlikely we're going to see the same thing on the distribution system. And it's actually going to be even faster on the distribution system, because distribution assets turn over much faster than transmission assets.
Mm-hmm.
Transmission assets are built typically for a much longer lifespan than distribution assets.
Mm-hmm. Yeah, got it. Okay. Yeah, that makes sense. That'll be interesting. So I guess maybe on that note, then, I'd be keen to understand if you want to maybe lay out what your thoughts are for, I guess, the trends in the industry and things at large that are happening and going forward in the future. Like, what are you excited for? What problems do you see being solved the next, now that this problem is solved and can be kind of rolled out? Just very keen to understand your general thoughts, being an expert in the industry.
Yeah, so I'm very excited. There's all of this talk about the energy transition, right? We're transitioning from fossil fuels to cleaner sources of power. And obviously that's a fantastic thing to have happen. And we're also seeing consumption change from petrochemical based to electric based, right? The big one that's happening now, transportation, EVs are becoming much more commonplace. Most of the major car manufacturers have a plan in place, and it's not like a 50-year plan, it's a near-term plan to dramatically increase the number of electric vehicles that they sell. Very exciting times. So there's this energy transition happening, and it's not just going to be transportation, it's going to be in industrial processing and a lot of other spaces. And I think the key thing that folks are starting to realize is that part of the energy transition has to be a digital transformation of the grid. We can't, we're moving away from the volcano model, and the volcano model didn't have a whole lot of sensing. It didn't have a whole lot of instrumentation. It was overbuilt and reasonably reliable. But as we start changing up the entire scenario, the entire game, we need, for the energy transition to actually happen, we have to digitally transform. And that means we need to think of not only moving electrons in terms of a voltage and current, but we have to think about monitoring the grid continuously in high resolution. It's about moving bits as well as electrons.
Mhm.
And like
Yeah.
that has to happen. Otherwise, the energy transition is DOA. And
Got it.
there are effective, efficient ways, and there are very bad, very slow, very expensive ways of doing this. And like, hopefully, fingers crossed, we go down some of the more effective, efficient pathways for this transition.
Yeah, got it. Okay, that's fascinating. Yeah, I think that that makes sense, and I feel like it's very exciting, obviously, to think about becoming a much more digitalized society in general, because there's so many benefits to being able to have access to this data to find room for improvement. I think that the biggest thing I've learned from doing this podcast is that there's so many of these problems that people actually didn't even know were a problem. And as soon as you started collecting data, which is kind of the baseline for everything, it allowed for observing what is going wrong here and how can we fix it. So I think that'll be fascinating. Um, I know some people are not a fan of big data, but I think it's quite interesting. I'd be keen to understand. I feel like there's probably not too many, but are there any major items in terms of regulatory regulatory compliance or things that you see coming down the pipeline that might affect this industry and specifically what you're doing at PingThings?
Oh, I mean, it's a very good question. This industry and its regulation are like completely coupled, right? This is regulatory behavior drives the behavior of the industry. So for us, we, and new regulations typically take years, right? There's a very complex process, a lot of give and take, and it takes years. And so from PingThings perspective, right, we don't have a 5 or 10 year plan. As a startup, we've never had that luxury. So we believe that, there is a drive in the kind of regulatory space to more data is good, but more data typically means a higher cost for utilities. And so there will always be pushback.
Wouldn't there be, if this data is able to be collected, wouldn't the cost savings offset some of the cost of having more data?
So you're applying a simple rational model to this, but it's not how the industry works, right? A lot of the utilities are monopolies. You can't like easily switch your power from one provider to another. There's all sorts of complexity. So saving a utility money could be completely meaningless. As irrational as that sounds, utilities make money doing certain things, right? They are granted a particular rate of return on capital that they spend. And so the incentives aren't necessarily like, oh, hey, saving them money, they'll buy that in a heartbeat. It doesn't work that way a lot.
Got it. Okay.
Oh,
Do you have any thoughts about how this could be solved? Like this idea of misalignment, because I think that incentives and alignment there are super important. It kind of goes into this item with the regulatory aspect. Usually, is sometimes regulations have oftentimes have good intentions, but oftentimes also create kind of adverse outcomes because the incentives are misaligned. So I'm curious if you have any thoughts on what the future might look like for utilities as a whole and changing that incentive structure, or is that even possible?
I mean, right, you're trying to change not just utilities, right? It's not like you're saying, hey, utility number one, we need to change you. The regulatory bodies create a set of rules, and those rules govern how the utilities can make money and how they behave and how they lose money. And so the utilities then try to operate in a way that maximizes their profitability based on that set of rules. So it's not just about changing the utility. If you have to change the entire, like all of it. And that's, I would generously say we have not figured out how to do regulatory action well. Like, right, there are hopefully better models than what we currently employ. There's room for improvement. Because as you said, when regulations are created, it's a multi-year process. So you've just created a set of rules that really was intended for 5 to 10 years ago and is now being applied to today. And if it's hard to change those rules that were intended for a world 5 to 10 years ago are now going to last another decade. So, like, obviously, this is that a great system?
Yeah, it's very difficult because it's the nature of change in the space would definitely outpace any regulatory changes that need to adapt with it, right? So I think this is an interesting problem. Maybe something a little bit too deep to go into now, but I think why don't we maybe shift a little bit? I feel like you might have some interesting thoughts here around. I guess generally speaking, I'm always curious to understand, because of your journey, what your thoughts might be on kind of the education space. And again, I like to focus this around for young professionals looking to start their career in some space that's kind of affecting positive outcomes for the climate. So in the climate tech space, what is your advice to them, to young professionals, especially if they want to maybe get into this industry specifically?
Ooh, so I'm actually pretty biased about this, but I think that when you talk about clean tech, right, immediately what pops to mind is like, oh, solar, or battery storage, or hey, I'm going to go work for Tesla in an electric car, and I think those are obvious. I think that if you really want to make a big difference, I actually do think, like, I'd love to see more talent going to the utilities, because they control power generation, transmission, and distribution in this country. And, you can't omit them from any of these solutions, any of these conversations. They're like the giant iceberg. And so I would say, if you're really passionately interested in making those types of changes, like, I think the electric utilities are a place where that sort of innovation-focused mindset, like, would be incredibly powerful. It's going to take time, but they're not to be ignored. They're not to be sort of abandoned.
Yeah, that's obviously a super interesting point, because, like you said, they can't be removed from the equation. But also, I think it's difficult because a lot of young people, when they think about, I want to make it go and do something innovative, they don't think about a utility. It's kind of the opposite, right? I wonder, this is something I think about a lot too, is kind of the relationship with government, small governments, specifically like city governments, and being able to be a little bit more nimble, but not too nimble, of course, right? Because that's not what we want out of a government, is to be too changing, right? That's interesting. I guess what are some of the things that you look for when you're hiring for your team? Do you care a lot about kind of degree, background? What are the big things when you're making technical hires that are really important to you?
Ooh, that's a really good question. We don't care a lot about background, right? Like, oh, you went to Harvard, whatever. We care about raw intelligence, kind of like horsepower. We care about sort of openness, in terms of, you want to grow, you want to evolve, you want to learn, and you're curious and you're asking questions. So, like, pedigree and like where you went to school is we don't care about. And so we tend to attract a relatively unique type of person, because it's got to be about personal growth. And the folks who come to PingThings, they come to PingThings because they're typically they're really smart, but how they want to grow and how they want to develop and the direction we want to grow is well aligned, so that everyone's incentive is also aligned and it can work, right? So when you're going to go to some job, you want to find a culture where you can thrive and where you can sort of be the best version of yourself. And that's something that's actually pretty important to us, because you can always go make more money at Facebook.
Mm-hmm.
I mean, and you can make a lot more money. It's the delta is dramatic.
Mm-hmm.
And so the people who choose to be here are talented, but they're also driven by a different set of values.
Yeah, I think it's important when company building to think about the culture you build, right? Whether you're just attracting mercenaries, right, who are going to go for the highest bidder, or if you want somebody who's really bought in for the vision. Because from a talent perspective, obviously that's my day job. Seeing companies just try to attract people because they can pay them more right now or whatever, that doesn't necessarily end up in long-term success. Obviously, people should be paid well, but it doesn't have to be these kind of crazy numbers where people are, poaching from just the other top companies, right? I think it's fascinating. I guess I'm also curious, maybe because you had made a comment earlier about your experience with your MBA program. I'm curious, what are your general thoughts on kind of the education space, especially what the universities are doing and whether university is actually kind of worth it, if you will, at this point in time? Say, for example, somebody who wants to become a data scientist, right? Or some other kind of, software related kind of profession. Do you have thoughts on whether or not it's worth it? Maybe the model should change. Any kind of ideas there?
Oh my gosh, such a big can of worms. Obviously we're in an educational bubble. When you have cheap, easily available money, that's what happens over and over and over again. We just keep relearning the same lesson, or maybe not learning it at all. I think that in computer science and software engineering, it's kind of a fascinating space because everything you need to know is actually available for free, right? You don't need to go to a walled garden. You don't need to go to Harvard to learn computer science. Actually, it's all hell, there might even be better materials for free online with better instruction. And so, and also the community itself in software engineering, all of those smart nerds tend to be unbelievably generous with their knowledge. So when you look at law, or you look at finance, or you look at medicine, right? They've constructed all of these artificial barriers to entry so that they can retain sort of high incomes.
Mm-hmm.
Medicine's not hard. It's expensive, and it's a walled garden that you really have to crack to get into. But it's not hard. It's not intellectually demanding, but it's really well paid because they have a heck of a union, a heck of a lobbying firm, and they've enacted laws across the country to kind of protect that. Software engineering is not like that, thank God, at least not yet. And you don't need a college degree to be an amazing coder. You need to be smart. And we find that there's great talent that's both trained academically, and there's also phenomenal talent that just taught themselves how to code.
Mm-hmm.
And so I think in that space, in the computer science, software engineering space, I think that's the one place where there is value for the academic degree. I think in a lot of other areas, there's just not much bang for the buck.
Mm-hmm. Yeah, I think it's fascinating. I think that it's hard for a lot of people because there's like I remember specifically growing up that there was so much pressure from outside. Thankfully, not within my family, but there was a lot of pressure from everybody outside to go to university. It was kind of like that's what you have to do, right? And I ended up, of course, not going to university, and I think I've turned out things have turned out okay for me. But I think a lot of people have a really hard time when they're young with having all that pressure pushed on them to go do something when I think your story is maybe an example when you don't exactly know which area you're super fascinated by yet, and you don't know which area you want to go down, right? Hence your kind of entrance to you had thought you were going to go down the med school route, right? And then ended up changing ideas, right? So I think I feel like there's definitely a bright future for changing the education model and helping people identify what they want to do before they really go in deep study into something. But I think this is really good. We've talked about a lot of interesting things. I think you've really done a great job of helping understand some of these super technical things for somebody like myself who knows none of this. So really, really appreciate that. Are there any final thoughts or items you want to leave us with?
Yeah, actually, there's another comment I'd like to make on the educational topic.
Mhm.
So everyone's talking about, oh, we need more STEM, we need more STEM, we need more STEM, right? Science, technology, engineering, math, medicine, whatever the M stands for. Oh my gosh, we need this. And I'm actually, I I'm very biased. I think it's very important to understand how the world works from first principles. But when you look at STEM jobs, they don't they're not like overwhelmingly great deals, right? And I'll give you an example. Computer science and data science are the exception, right? You can go make a shocking amount of money by being an excellent computer scientist or an excellent data scientist, right? When I initially did my undergrad, that simply wasn't the case. If you got an electrical engineering degree and at that time, and you had a 30-year career, you capped out at like 80K. There was
Mhm.
there was no money in it. And the ironic part is that space is hard. Like you need a good amount of intelligence to survive and thrive in a lot of the physical sciences, right? They say to be a PhD in physics, average IQ is like 139,
Mhm.
right? But they don't, physics doesn't pay. Power engineering, it doesn't pay. The smart people, the people who kind of understood how things worked, what did they do? They went to law school. Why? Because you come out and as a first year associate and you made like these days, it's like what, 185, 200?
Mhm.
And you're like looking for misplaced commas in documents that the partner wrote. Like, I mean, why would you kill yourself for a super hard degree like engineering and then go make 80K a year when you could go crush in a space like medicine, go become a radiologist for 400,000 a year, or even better, go to like finance. Like the talent, assuming you have equal knowledge of the possible outcomes, talent goes where the money is. And the money isn't in those traditional STEM spaces. All of the STEM people who are really smart wind up going into software and data science because it pays like sometimes
Mhm.
10x more.
Mhm. Do you anticipate that changing that those other
No,
areas will get paid more?
nope.
No.
Why?
Yeah. I think I will say from a recruitment perspective, I have noticed that power systems engineers, their salaries have increased significantly over the past few years. That's an area I've recruited a lot in. And it's mainly because of these grid issues, right? They need smart people to work on these, and there's not that many out there. So that's one area I would say has been increased, but I don't think it's I would agree with you, it's not met the data science side of things. But this is very fascinating. Anyways, again, really, really appreciate you coming on, Sean. Any final thoughts where people can reach you? Anything else you're looking for?
Yeah, we're always looking for like we're always hiring. We are, and we're always looking for new customers, new collaborators, new partners. And we're very excited with the trajectory we're on with regards to the energy transition. We just want to speed it up.
Absolutely. Yeah, I think there's so many great things happening. It sounds like overall you guys have a really, really solid team doing some pretty great things already. So I'm excited to see how it continues to grow. And yeah, thank you so much for coming on, Sean. We'll definitely have to have you again in the future.
Yeah, thanks so much.
All right, thank you so much for tuning in to today's episode. Please let us know what you thought of the show. Share your thoughts with us on social media, or feel free to reach out to us directly. And then, of course, we always ask, please share this with at least one person who might find it interesting, since our entire goal is to help spread awareness of the different solutions out there that to help kind of advance the world towards a greener and cleaner place. And please, of course, consider reaching out to Sean on LinkedIn to learn more about PingThings and what they're doing. Perhaps you're somebody who works at a utility who might find this interesting. If you are joining us for the first time, please, of course, as always, subscribe and turn on notifications to be made aware of future episodes. And then we do really appreciate any ratings and reviews that you can give us on the various listening platforms. And if you're interested in becoming a sponsor or want to collaborate in any way, you can reach out to me directly. My email can be found in the description. And if you want to get more involved in the climate tech space in general, feel free to join the Slack channel we've created or comment on our LinkedIn page. There's a lot of other climate tech professionals who interact with us there. And on a quick note, for next week's episode, we will be sharing our conversation with Rekha Sharma, who is the founder of Solve4X, where she's helping solve the energy demand issues that are continuing to shake the grid with the electrification of industries. Currently, her focus is primarily focused on EV charging. So this is a really fun conversation in general with a founder who's actually quite early in her journey. So there's a little bit of a kind of change of pace. So definitely stay tuned for that next episode. And again, thank you guys all so much for listening to the CleanTechies podcast, and we will see you next time.